He will not form this
So I'm one of those people that Joe was talking about who works on the messy stuff in these computer simulations and tries to understand how to better model the complex physics that is often subgrid. So simulations of collisionless dark matter have played a key role in establishing the concordance cosmology that a lot of it was described to us earlier by John. So it has completely transformed our perception of the universe. Our universe is dominated by dark energy, and galaxies owe their existence to a particle that we've yet to detect, so dark matter. And here what you're seeing is a chunk of the universe, but just the dark matter in that chunk. And what you see is the result of those tiny fluctuations in the cosmic microwave background that Joe showed us earlier, growing under self-gravity in an expanding universe to form this magnificent cosmic web. And as we've been told, what we believe is that this dominates the matter density in the universe. The gas follows this cosmic web, and it collects in the nodes of this cosmic web where, unlike the dark matter, the gas is collisional, so it's allowed to radiate energy, cool, and eventually become denser, and some of it eventually might turn into stars. Now, why do we believe this picture? What is one of the reasons that we believe the picture that the universe, the dark matter, this invisible material, is structured in this way? We believe it because if we associate with each of the dense concentrations of dark matter in a simulation like this with a galaxy, we very nicely reproduce the structure of galaxies in the universe. So we saw a picture, John showed us one of these from a survey. And so in blue are maps of the sky from observations, so from deep redshift surveys, so where you look out as far as you can see with your telescope and put a point on your map with a redshift position giving you the 3D and spatial information. And the thing is that if you compare these observations to the prediction you get from these dark matter only simulations where you simply paint a galaxy everywhere where you have one of these dark matter concentrations, in a statistical sense, you very nicely reproduce the distribution of galaxies in the sky. This is considered one of the big successes of dark matter, cold dark matter theory here. Now, Joe showed us this picture, and what he told us is that so this is a picture of the mass function, so the number of objects you have of a given mass. Okay? Now, if you simply count how many dark matter halos you have, and you plot it, you would get a line that looks like this. But this line here is now scaled by the baryon fraction in the universe. So this is the prediction you would expect if you believed that you would form more stars in dark matter halos that are bigger, okay? So very simple assumption. Bigger halo, bigger dark matter halo, I collect more gas into it, I'll form more stars. But the reality, if you count the number of galaxies you have as a function of their stellar mass and put it on a plot like this, the reality that Joe told us is that you are vastly off the prediction from the dark matter simulations. So both at the low mass end, you have fewer galaxies than the dark matter simulations predict, and at the high mass end. And Joe gave us an idea for why this might be happening. So I'm not going to talk about the AGN, the supermassive black hole formation. I'm going to talk about the star formation aspects of this. So when you see this mismatch, the simplest thing, predicting in a dark, we could predict very nicely where galaxies should sit in the sky by associating a galaxy to the dark matter halo. But what this picture shows us is that we do a terrible job predicting how many stars should form in a given dark matter halo. Okay, so that's the goal of what I want to get at in this talk. So you realize that this is a difficult proposition when you start looking at things like pictures of galaxies. So here's just a compilation of galaxies from the Hubble Space Telescope, and you see that they come in a wide range of morphologies and colors. You've got ellipticals, you've got spirals, and this becomes even more complicated when you look close up at any individual galaxy. So here's a picture of M83, which is a beautiful spiral galaxy in the southern hemisphere. It's a picture from the Hubble Space Telescope. And what's nice about this picture is that there's a zoom in on a region of that galaxy. And so what you see here is star formation in action. So the dark lines here are your dust lanes. And on the edges of those dust lanes, you see these red pockets of light, which are where the newly born stars are just forming. And as they form, they're emitting radiation and heating the dusty cocoon that they're sitting in. So they're radiating in this reddish color. And eventually, we think they're emitting so much winds, fast-moving winds from these particles, that they clear out these cocoons, and you see here the naked blue clusters, newly born clusters of stars. So here you really see a time sequence of the stellar evolution in action and the complexity of it. And you say, well, no wonder we can't predict from the simulations how many stars should be forming in a given dark matter halo when you see this. However, one of the most remarkable correlations comes from doing measurements of the star formation rate, surface density, and the gas density. So this is a very famous plot by Rob Kennicott, 98. So he was here a few days ago speaking about this. And so, astronomers, we'd like for these measurements here on the axes to be densities rather than surface densities, but of course we're only seeing projections in the sky. And so what you see here is that when you measure the star formation rate surface density and you plot it against the gas surface density in galaxies that span different environments, so from normal disk galaxies to the centers of those disk galaxies to starburst galaxies, what you find is that they lie on a very tight correlation. And this, of course, is astounding given the complexity of the star formation you just saw in the previous image when you look at the reality. And what's even more astounding is when you realize that these measurements were made on kiloparsec scales. So in other words, the observations are you look at the galaxy on a kiloparsec scale and you measure the rate of star formation and you measure the average surface gas density on a kiloparsec scale, but yet we know that star formation is happening on subparsec scales. So it's even more remarkable that you have this correlation on a kiloparsec scale given that the actual star formation is happening on much smaller scales. Now, you can fit a nice line to this. So here it is, the star formation rate, surface density goes like the gas density to the 1.4 power. And you might interpret that as telling you how star formation happens. Is this telling us how quickly the star formation happens in a galaxy? And so the argument here goes, the rate at which star formation happens might be proportional to the gas density in that cell divided by the free fall time of collapse. So imagine the simplest thing, a sphere of gas of uniform density, and imagine it collapsing under its own gravity. The time scale on which this happens is this free fall time. So the important thing, forget about all the constants, is that it just goes like 1 over rho to the 1/2 power, which means that if you believe that star formation is happening on this time scale, so when you divide this density by the free fall time, you very nicely get out that the star formation rate scales as the density to the 3/2 power. So this is intriguing, of course, because 3/2 is very close to 1.4, right? And perhaps this is all you need to understand how quickly stars form in galaxies. Okay. However, in recent years, there's been a push to observe galaxies in different wavebands. Okay, so I'm giving you an example here of one particular galaxy. So here it is, NGC 6946. And it's imaged here in different wavebands. So here's a picture of what it looks like in dust emission. So dust is something that we believe gives you a picture of what the galaxy, what the recent star formation looks like. because the gas is heated by new stars, just like you saw in that previous image with the red cocoons around the new stars. So here's a picture of the same galaxy, but in H-alpha emissions. So this also is believed to be a tracer of recent star formation. Here's a picture of that same galaxy in atomic gas. And finally, a picture of that same galaxy in molecular gas. And the striking thing about these pictures is that the one, the most, you see very clearly, you don't have to do more quantitative assessment, you see visually that the component of the gas that is most correlated with the recent star formation is the molecular gas. It's not the atomic gas, it's the molecular gas. So if you want to do a better idea of understanding how the stars form in the galaxies, you have to think about the molecular gas in these simulations. So one of the questions you might ask is, is the molecular gas inside galaxies, are they long-lived structures, or do they disappear after a certain amount of time? And so you quantify that by thinking about lifetimes of these molecular associations. So here I use the word molecular cloud, but as I go on, you will see that cloud is perhaps not the way you would best choose to describe these associations. So of course, we can't go and measure lifetimes. We're doing astronomy here. So we have to think of clever ways to figure out lifetimes of these kind of structures. And so one way is to use galaxy dynamics as a clock. So here's an example of M51, so another spiral galaxy. And the symbols here represent molecular cloud associations of different masses. So the large circles are the most massive, 10 to the 8, and the small little green dots are the smallest ones detected for this galaxy, so 10 to the 5 solar masses. And what you see is that the large structures really line up with the spiral arms. But in between spiral arms, you see a lot of these little green, small molecular clouds. And you either believe that these small ones formed there, or if the alternative is that you believe that most of the molecular associations are gathered and form in the deep potential well of the spiral arms. But as that potential well revolves in the galaxy, the clouds that pass through this spiral arm get shredded and eventually end up in the interarm regions. And of course, if you have an estimate for how quickly that spiral pattern is moving, that gives you an estimate of the lifetime of how long it took to transit from the deep potential well to these interarm regions. So an estimate of about 100 mega years for these massive molecular cloud associations. Now it turns out that if you do similar exercises of figuring out the lifetimes of these clouds, you don't always get 100 mega years. Okay? So a lot of it, we think, depends on the mass of the molecular clouds. So here's an example of close by, so a molecular cloud that sits in the Milky Way, Taurus Auriga. And here, the trick for estimating the lifetime of this molecular cloud is to search for the oldest stars you could find associated with the gas. And when you do that, you find no stars older than 5 mega years. So that immediately tells you that this molecular association can't be much older than that. Okay? And this also gives you, so the idea for these little ones is that they're in a highly dynamical state. And so one ongoing idea is that they form by colliding flows of atomic gas that then gets transformed into molecular gas. But we'll come into that, the dynamics. So we could go back to this Kennicott plot of the log of the star formation rate surface density, except on this axis, rather than just plotting the log of the gas surface density, we can divide that surface density by the free fall time of given objects. Okay, if this was the natural time scale for these clouds to collapse and form stars. And what you find is no matter what star-forming objects you plot on this graph, they all, again, follow a very tight correlation. So here in these contours, these are the original Kennicott galaxies that you saw in the 98 plot. But also what's plotted here, these red points are individual molecular clouds, so not entire kiloparsec regions in a galaxy, but individual molecular clouds in a galaxy. There are There are molecular clouds from high redshift disks and high redshift starbursts still falling on this relationship, along with even more low redshift galaxies, okay? So the key thing is that they all lie on this relation. And if star formation was happening on a free fall time scale, you would expect the slope of this line to be unity, right? But what you find is that the slope of that line is about 0.015. So as John said earlier, this is a big failure. Star formation is incredibly inefficient, right? Only about 1% of the gas gets turned into stars on a free fall time in these galaxies. The other thing you learn is that if star formation proceeds at the same rate as indicated here, if it were to proceed at that rate for all time, you would need about 100 free fall times, right, to convert all the gas into stars. But what we saw from the time arguments is that those molecular clouds don't live for 100 free fall times. So what it's telling you is that somehow these molecular clouds form, produce stars, and then vanish or disappear or become inconducive to star formation. So there's a dynamic in these molecular clouds. There's a hint of the dynamic. So you start to see it when you start looking, again, by eye at the structure of these molecular clouds. So here's a map coming from, so we don't normally think of Planck as giving us maps of the molecular gas, but that is another beautiful use of the Planck data. So here you have an all-sky map of the carbon monoxide. So imagine you're sitting at the center of this sphere and making a map of the molecular gas in the sky. And what you find is that the molecular gas is concentrated in the galactic disk. And already you have hints that it's quite filamentary. And this becomes even more obvious when you zoom in on any given local molecular cloud. So here again is the torus molecular cloud. But here it's color-coded by velocities. And so this is very interesting because it tells you is not only does it look like a mess, but the dynamics is a mess of these molecular clouds. So here I think the green is everything moving between 0 and 5 kilometers a second. The blue is between 5 and 7 kilometers a second. The red, up until 12 kilometers a second. So you're seeing that there's vast dynamics. You can quantify the dynamics of the molecular cloud by making this famous plot. So this is what is called the line width size relation in molecular clouds. And so the way this plot is made is you choose regions of a given scale length, which you plot on the x-axis, and within those regions you measure the average velocity dispersion. And you find this trend that on larger regions there's more velocity dispersion than on smaller regions. And so knowing that molecular gas is very cold, so about 10 Kelvin, which corresponds to a sound speed of 0.2 kilometers a second. What this shows you is that not only are the gas in the molecular clouds moving, not only is there a lot of dynamics there, but it's supersonic, right? The material is moving at velocities higher than the sound speed in the molecular clouds. So this is evidence for compressible supersonic turbulence. The slope of this line would be different than 0.5 if it was incompressible. Now, when you look at where the stars form in a molecular cloud, you notice that they don't form randomly in a molecular cloud. So here's an image of, so this is from the Core to Disk Legacy Survey of Spitzer of the Perseus molecular cloud, okay? And then gray, you have these are extinction contours, so they give you a sense of what the density is in this piece of the molecular cloud. And in color, what you see are so the newly born stars that had not had time to move out of the region where they were born. So what you see is possibly what you expect is that the newly born stars, which haven't migrated yet from their birthplaces, are really clustered in these high density regions in the molecular cloud. And it becomes illuminating to go back to this plot of the line width size relation, because what you see is that the place where the sound speed where the velocities transition from being supersonic to subsonic can be associated to a length scale, right? Which we can call the sonic scale. So this is where you transition from supersonic turbulence, which is on the scale of about 1/10 of a parsec. So here you have your sonic transition from supersonic to subsonic. Now this is one of my favorite observations and the motivation for a new way of trying to model star formation. So ignore what's on the right-hand side here, and let's just look at this map here. And what it is a map of is the velocity dispersion in the vicinity of a protostar. And so we said that 10 Kelvin, so where you transition to becoming subsonic, corresponds to about 0.2 kilometers a second. So the dark colors here are 0.7 kilometers a second. So what you see here is that exterior to the region where the star forms, you have supersonic motions, and somehow there's a transition to this subsonic regime, and it's there that the protostar decides to form. So this has been, there's been this very poetic term to describe this, so these regions of these islands of calm in a turbulent sea. That's where the protostars want to form, at least in the observations. Now, one troubling thing about this whole picture is that isothermal supersonic turbulence, compressible supersonic turbulence, is known to decay very rapidly. Okay? So the question you might ask is, how do you sustain this kind of turbulence in these molecular clouds? And so here people invoke the kind of, there are many mechanisms associated to stars that could possibly drive this kind of turbulence. So of course, jets from newly born stars, supernovae, H2 regions, stellar winds. These are all things that can drive this kind of turbulence. But of course, the problem is that you also find molecular clouds, such as this one. This is a non-star forming molecular cloud, Polaris flare, which has turbulence. Clearly, you could see turbulence in this picture. And there's no star formation. So are there ways out of that? And again, here, rather than invoking local processes to drive turbulence, you can start thinking about the fact that these molecular clouds sit inside galaxies where there are global ways to transfer things, transfer energy from large scales to small scales without the need for star formation at all. So just getting the energy from, in this example, the shear rotation in a self-gravitating disk. And so here you see a picture from an idealized simulation where, so differentially rotating, if you zoom in on one of these regions in this disk, you can see what the theorists would call molecular clouds. And if you do these kinds of simulations on even higher resolution, you see that these non-symmetric structures, which are gravitationally interacting in this differentially rotating disk, can transfer some of their kinetic energy and impart this energy cascades to give some kind of fragmentation, so a turbulent structure interior to these molecular clouds. So there are mechanisms other than the obvious to drive turbulence in these clouds. So my question for my talk was, how do galaxies know when, where, and how quickly to form stars? So we had this, the idea that comes from this kind of relationship, right? And one could imagine that if one could identify regions of gas above a certain threshold, so already there's a parameter, a threshold, and use this recipe motivated by the Kennicutt observation that star formation rate proceeds at a rate proportional to the density divided by the freefall time, you know that this constant here can't be unity. The observations tell us that it has to be small, very small. So you can conceive that this could be a way to run, to model how quickly stars form. So this answers the question where, right? So where at the high density regions, when a region gets to that high density, and how quickly? Well, it happens at this rate, but not at the free fall time. We want to slow it down. We want to kill it till it's only 0.01 of that. So you could do it that way, or you could try to think about what the molecular clouds are telling us. So one thing that is well known from from the simulations, so both theoretically and observationally, is that isothermal supersonic turbulence follows a very specific density probability distribution function, so a log normal. So here, if you take a quiet, so a region of a molecular cloud where there's no star formation happening, you can make a histogram of how much gas you have of a given surface density. And the theoretical prediction is that you would get this green line, so the log normal, and you see here that in this measurement is the black histogram, right? So very nicely follows this log normal. And the log normal, of course, can be parameterized. There's a mean and there's a width, okay? So very simple function. Now the width of this distribution tells you what the density contrasts are in the gas, right? It tells you, so the wider this distribution, the denser, the more dense gas you have in your simulation, as well as the more rarefied regions you have in your simulation. So it makes sense that the width of this distribution is somehow connected to the Mach numbers in these gas clouds, so, which is, of course, a measure of the velocity, the bulk velocity divided by the sound speed, right? So you expect that you have large Mach numbers, you're able to compress the gas, and both have rarefied regions, extreme rarefied regions. Well, it turns out that the width of that distribution does not only depend on the Mach number, it depends on at least one other parameter, actually probably a third one if you include magnetic fields, but I'm ignoring that here. And so it depends on how the turbulence is driven. And so it turns out that if your turbulence is coming from what we call solenoidal forcing, which tells you how which is produced by rotational motions in the gas. So here you can invoke things like a differential rotation of a disk. You will get a very different density distribution than what you will get if the forcing, the thing that's pumping energy into your molecular cloud, is coming from compressive forcing. So here, even more candidates, right? So supernova, all the things that give you compression. And again, without making PDFs, you see very clearly that there's a big difference that in the case of compressive forcing, given the same amount of total kinetic energy input into the system, the case of compressive forcing, you will get a wider range of densities achieved in your volumes. You will get both higher density regions and very empty regions compared to the case where you have solenoidal forcing, where you see the turbulent structure, but it's much more uniform. And this, of course, appears very nicely in is consistent with the kind of PDFs that you measure. So you see in the solenoidal case, the width of your PDF is narrower than in the case where you drive the turbulence with these compressive modes. So you can parameterize this histogram, the width of the histogram, with not only the Mach number, but also this number that tells you how much forcing you have in these two different modes. Okay, so this gives an idea of an alternative way to figure out how quickly to form stars in a simulation. And so the cartoon idea here is that you figure out below which length scale the gas transitions from a supersonic to the subsonic regime. And so it turns out this length scale is very much what Joe was telling us about when he talked to us about the gene's length. Okay, so it's when the gene's length is comparable to the sonic scale. So there's a transition to turbulence. And that corresponds to a density, a critical density. So here I'm using S for density. And so the idea here is that if there is this universal density distribution of gas in turbulent molecular clouds, once you know what this critical density is, you can simply count the gas that's above that threshold density to get a sense of how much of your gas cloud will turn into stars. And now, so this gives you a sense of the efficiency of star formation, except that before, where it was a single number, 0.01, now your star formation efficiency depends on the dynamics of the gas around it. So it depends on the Mach number, right? Because these are the quantities that determine how wide your density distribution is. So it depends on the Mach number, it depends on what kind of forcing you have, and it also, this transition threshold depends on what we call the virial parameter, which is just a measure of how much kinetic energy you have to gravitational energy. Now it turns out when you do this calculation, to be fair, you're not computing the stellar initial mass function, which Joe talked about earlier. Well, first of all, you have to have incredible resolution to get to the level where you're forming individual stars. But also, so even taking into account the complexity of the star-forming gas, with this kind of method, you would only be getting a prediction for how many dense clumps you'd be forming in your gas. But it's believed that the dense core mass function, which is here actually measured in an observation, is very similar in shape to the stellar initial mass function. It's just shifted by a certain constant. So there's still, even trying to do things, taking into account the turbulent properties of molecular clouds, there's still a parameter here, so on the order of 30 to 50%. So as I said, rather than the efficiency, so being just one number, your efficiency, your star formation efficiency per freefall time, will depend on the dynamical properties of the gas in very sensible ways, right? So if you, for example, consider, so here we fix this, the mixture of solenoidal and compressible modes, but we could think about what happens when we vary the virial parameter and the Mach number, and so I won't go into it, but just to show you that the efficiency is not a constant, it varies with these parameters in a sensible way, so that, for example, if you consider for a fixed amount of gravitational energy how the efficiency varies with Mach number, you find that when the Mach number increases, your star formation efficiency increases, which makes sense, right? Because you're compressing more gas in your simulation. So to come back to my question, how do galaxies know when to form stars and where and how quickly to form stars with this kind of thinking? So the when and where question is answered rather than by saying above a certain density threshold, it's answered by looking for which regions in the gas have lost gravitational support, right? So you have two things that could resist gravity. You have the non-thermal motions here given by sigma, and you have the thermal motions. And when those motions can't withstand the pull of gravity, those are the places where you can say, I'm going to form stars, right? So it tells you both when and where. And again, you could go back to the simple-minded recipe motivated by the Kennicott plot of forming stars at a rate proportional to how much gas you have there on a free fall time. But now this efficiency parameter depends on the dynamics of the local gas near the place where you think your star is going to form. So you saw that the sonic scale, the place where we form stars, is 1/10 of a parsec. Okay? So this kind of thinking is not something that you can apply to any cosmological galaxy formation simulation. You have to start to reach those kinds of resolutions where the structure of your molecular clouds, you're actually modeling some of that dynamics that you expect to observe. So I'm going to show you our first attempts very quickly to show you whether this kind of alternate way of thinking about how to do star formation makes a difference. So these are not from a large volume cosmological simulation, but from what we call a resimulation. So it's a zoom simulation where we model, we take, again, a piece of the universe, but only in one region where we know a galaxy is going to form. We put all our resolution in there with this adaptive mesh refinement technique. And the galaxy I'm going to focus on sits here at the intersection of these filaments. So in here, in green is the gas density, in red is gas temperature. This is a 3-color image. And in blue are metals. So we know that stars form supernovae that release metals, okay? And what I want you to see by looking at this picture is that the galaxies sit in a complicated cosmological environment, right? They're not sitting, especially in the high redshift universe, so this is in the high redshift universe, they're not, in general, sitting in a tranquil region of the universe. In general, they're being fed by these cold streams along which come these substructures or satellite galaxies, and it's a very complex process. And so we play with this kind of thing, different simulations, different feedback, but I'm only going to focus on 2 simulations here to show you whether trying to play with the star formation recipe matters. So there will be the identical simulations, and we're going to be looking at just this galaxy sitting here at the intersection. So I'm going to only show you zoom-in pictures of this disk galaxy at the center. And the only thing I change in the simulation is this recipe for forming the stars. So here's a picture of the galaxy where I choose to form my stars by the simple-minded density threshold with a uniform, very low efficiency, okay, on a free fall time. And here's exactly the same simulation, so except with this different criteria, where I only form the stars where I don't have support, where I lose support against gravitational collapse. And again, this is very visual. You see very clearly that there's a huge difference in the kind of structure that you get. So you see it when you're looking at the galaxy face on, so much more fragmented disk. You see it when you look at the galaxy edge on. So here's with the old kind of star formation thinking. Here's with the new prescription. You see a much wider disk where you're starting to get more velocity dispersions. And so in a nutshell, to wrap up, what's going on here? So what we think is going on is that when you form stars by this density threshold, you preferentially always are removing gas and turning it into stars in the center of these galaxies, okay? And what that means is that you quickly form stellar bulges inside these galaxies. And we know that stellar bulges stabilize disks. So it's no accident that in the runs without in the run where you don't preferentially form the stars just in the high density regions, where you have a different criteria for forming the stars, you get more fragmentation. And it's because these disks are less stabilized by a stellar bulge. Okay? So by changing the criteria of when and where the stars form, you allow the gas to wait before it forms stars. You allow the gas to wait until it reaches higher densities. So in the simulations, and this has implications for where the stars tend to form. So rather than only forming, so you see in this picture, right, you see these dense clumps, has implications for where they form, and all of this affects the dynamics of the galaxy as well. So I didn't say it, but you can imagine the coupling here with the energy that's released from the stars. So just by changing where the stars form and how many of the stars form in one go, also will couple with how those stars release energy to their environment. So you can guess, without me showing you the plots, that in this kind of simulation with these clustered regions, the impact of supernovae going off in these cluster regions will be greater than the impact of the supernovae going off from stars spread all over. So there's a tuning just there in the, by changing where and how the stars are forming, you also change the impact on how the energy is input back into these systems. So I'm going to end because it's so hot in here, and just end by saying that it's clear from the observations that the star formation rates are not controlled by just one parameter, the density. There's a complex dynamics, and you can, again, this is all, as Joe said, how do we move on in understanding this? Well, part of it is, keep looking at the observations, look at those molecular clouds and try to understand what the data is telling us about the dynamics of them, and push the resolution and change your recipes of how you're modeling these things to account for the fact that, what nature is doing and whether you can capture it, that resolution. So I'll end there. Thank you.